Hello, students. Today we would like to discuss some financial models. We've been studying exponential and logarithmic functions, their properties, and mainly how to solve equations that involve these functions. And what we'd like to do today is to investigate some of the basic financial models which we can construct using these functions. I think you'll find this to be a nice change of pace, and usually financial models have interest for pretty much everybody because we are always confronted with finance in our lives, regardless of what career we choose. So let's get started. Let me share my screen. There are lots of terms here, but they're not difficult terms, and they're terms that you have some familiarity with. So I've tried to write these down so that they're very specific for you. Also, what I've tried to do is give you some ideas about how we actually construct these models so that it's clear that there's a mathematical foundation. Now, what we want to start with is something that's very simple, but very important, and that is simple interest. When we talk about simple interest, we're discussing an interest that is applied once. And when we think about the interest that we apply, we're considering an annual rate of interest or an annual interest rate, which we usually denote by a lowercase r. Please remember that as you look in other sources, the notations, the use of certain letters may change, but the actual formula is the same. So be aware that if you're reading different formulas from different sources, they may look a little bit different due to the choice of letters. We will always consider P to be the principal amount that is invested, and then T will stand for time in years, and that's relatively standard. Now, when we think of the interest being applied once, that's exactly what happens. And so we think of our initial investment P, and then we take the principal, we multiply it by the annual interest rate, and then the number of years T. Now, of course, we can factor the P, and this will give us a future value of P times the quantity 1 plus RT. Now, you've noticed here I've written A for amount. That's usually the letter that is used in the formula. Sometimes you will find FV for future value, but usually in our book, we will use the letter A, but we will also be familiar with the term future value. One thing that's important here, we often call P, the principal, the present value. So when we develop our formulas, we will be able to look into the future, solving for the amount, which is the future value, or if we are given some future value, we can turn the tables backwards and actually find the initial amount that was invested or the present value. So what we're going to find is that these formulas give us a lot of flexibility. And when it comes to finances, just like I said at the beginning, everyone is concerned with finance. So regardless of your profession, STEM or otherwise, these are very useful ideas to know. Now, again, the principal formula here for simple interest is very straightforward. What we want to do is now talk about compounding interest. That is, if we have a particular annual interest rate, we want to subdivide that. For instance, interest is applied n times per year. So what we do is we take the annual interest rate and divide by the positive integer n. For instance, maybe we apply interest 4 times per year, or monthly, which would be 12 times per year, or 2 times per year. The n can vary, but what we now have, we have constructed what we call a periodic interest rate, which we can often denote by lowercase I. So it's the annual interest rate divided by n, or N, if you like to call it, the number of compoundings per year. Again, we'll try to keep our notation fairly standard, but just remember that as you use, and I want to say this, as you use other sources, the letters can often change, but we're trying to keep standard, and I think you'll find these formulas in your book to be standard in a way that you can remember them. Now what I've done here is I've said, okay, just like we have up here, if we apply interest once, we're going to say after one period, we have the principal amount, and then we have the principal times the interest, the periodic interest. And when you factor the P, the amount that we have now is P times 1 plus I, where I, again, is the periodic interest rate. So what we think is that as we apply the interest, then we figure out how much money do we have. Okay, now we go to the next application of interest, which will be the second period. And notice I'm just using subscripts, first period, 1, second period, 2. Well, this is what we have for the first period. So what we do is we take that amount and then we apply the interest here to that amount, just like we did in the first period. So what you're seeing is when we factor the P times the 1 plus I, we have 1 and the I left over. And therefore, we generate a second copy of 1 plus I. So now for the amount after 2 applications of interest, we have P times 1 plus I raised to the second power. Okay, now that seems to be maybe setting up some type of pattern. Let's try it again. After 3 periods, this won't be any surprise. We take the amount that has accrued after 2 applications of interest, and to that we apply the periodic interest. Well, just, of course, not a surprise, when we factor the P times the 1 plus I raised to the second power, we're left behind with another copy of 1 plus I. So we see now that the amount after 3 periods or 3 levying of the interest rate, we have the corresponding power 3 here to the 1 plus I. So this is creating an inductive process. And many things that we do in finance and even in mathematics will produce an inductive sequence. And we will find that to be the case. I say sequence, that's the best place to study induction, because again, the domain of a sequence is the natural numbers. We will say much more about induction as we continue our STEM education in mathematics. But now what we can do, as I've said here, inductively, if we take M to be the number of compounding periods, say we just compound for a certain number of times, then using this pattern here, we would say after M compoundings, that is M periods of compoundings, we get P times 1 plus I to the M. So that's a very convenient way of keeping up with the amount, because it corresponds to the number of compoundings or number of periods. So when we say period, we'll think of compounding. So a levying of the interest will apply to 1 period, and that can be called a compounding of the interest. Now, you're thinking, well, do we just keep track of M? Or are the problems stated that way? Well, usually they're stated in terms of the number of compoundings per year and then the number of years. So for instance, what I've written here is we can replace M with NT. Again, where N is the number of compoundings per year and T is the number of years. So here's just a very simple example of this. Say we had 20 periods and our N was equal to 12. That is, we were compounding the interest 12 times per year. Well, we can simply use the formula here to solve for T. So M is equal to N times T. So T would just be 20 divided by 12. And now, of course, we can see here that the 4s will absorb, and we're left with 1 2/3 years or 5/3 years. Now, What that is basically saying, ladies and gentlemen, is that this would provide maybe a better way to state the formula for the future value when we compound interest. That is, write it in terms of NT for the number of compoundings. And then, of course, the I, which is the annual rate divided by the number of compoundings, we can just go back to what that was defined to be and write it here explicitly, as I've noted here. So now we can say the compound interest future value can be denoted by this particular formula. Now, what I've written here, we don't usually subscript the A with the NT where that the number of compoundings. We just usually write A. But again, it helps to realize that this is simply an inductive procedure, and we basically proven this result by induction. We didn't state the principle for mathematical induction, but that is not far from what we've done. So if you think about natural numbers and you think about, for instance, showing that something is valid for maybe 1 or 2, and then assuming the formula for some arbitrary natural number, you can use that particular hypothesis to show that the formula is valid for the successive natural number. That's really the well-ordering principle for the natural numbers. And that'll be something we'll talk about more. But when you think of inductive, you think of a domino effect. That is, once you establish a pattern, that pattern can be relied upon to give you information for larger values of the sequence. And we can think of our sequential terms as being the amount for each period. So again, that's an inductive procedure. Now, what I want to state is something that comes up in finance, and you will see this in your text. It is interesting, but certainly not something that you see every time you talk about financial models. But of course, if you end up studying more finance, you will, of course, see this again. But what we might be interested in is if we are compounding interest, what would be the corresponding simple interest rate? That is, if we just levied interest one time per year. And that's not a bad way to look at compound interest, because when you tell someone about simple interest and you give them that percentage, that can actually seem more real to a consumer, even more real to those that are well versed in mathematics. So we're thinking, what would be the corresponding simple interest that would actually provide the same level of outcome, the same future value? So what we do is we just simply replace T with 1. And we go to our formula, which is to say, if we're thinking of the effective interest rate as being the simple interest rate, where we have the P times the 1 plus R EFF, and then we move to the compound interest formula, again, replace the T with 1, we simply have this. So you're thinking that's really simple, and it is. The P's absorb, and then if you solve for the effective rate, you just basically subtract 1 from 1 plus R over N raised to the N power. So this gives the corresponding simple interest rate for the N compoundings per year. And that can be a really good way to compare rates. For instance, if you're looking at rates of different credit cards and things of that nature, it would just be a good way to say, well, what is the best value for what I need in my financial life? So again, right now, we have a way to compute the effective interest rate for compound interest. Now, there is one other mode of computing future value that we call continuous interest. Notice in this formula, ladies and gentlemen, that N is a finite number. And if you think about maybe things that occur in your life, when you think about credit cards and you think about financing homes and automobiles, there are other mathematical items that we won't be discussing, and those are annuities, in the sense that when we actually amortize buying a home or purchasing a vehicle, we apply the compound interest formula to create new formulas. But what's important here is we can allow the n to become larger and larger. And so you might think, does this mean that we're going to get much, much, much more money? Well, it would be nice, but that's not necessarily the case. You don't find this very often, but it does exist. That is continuous interest. So we're thinking we start with simple interest, then we compound n times per year, and we get a fairly simple formula that's basically inductive. Now, the only other opportunity that we have, if we're not going to talk about annuities, which that's just going to be a separate class, and if you're interested, I would encourage you to look into that. Again, we all are faced with buying automobiles, purchasing homes, buying things on time, where that will be applied. So that would be something of interest if you have time to do that. Now, if we allow n to pass to infinity, we get to think about some limiting processes that we've actually been doing throughout this class, especially with vertical asymptotes and horizontal asymptotes. These are very interesting calculus concepts, but they have a very interesting intuitive feel that we've been able to exploit so that we have a better understanding before we get to the calculus. So what can happen here is that if n passes to infinity, you're thinking, well, you've got the n here and you have the n here, but the p and the t really are not affected by the n, and of course the r isn't either. So you're thinking, what would the calculus do? Well, intuitively, what we want to think of is moving the limit inside, so we can actually focus on the variables that have an n dependence. So we factor the p, and then we use our laws of exponents. That is, the t we factor here, n times t, we can just factor using brackets here. And then we can pull the limiting process into the portion of the function here that actually depends on n. And that's something that you would naturally do, but this is based on the concept of continuity. We do our sign test, our BVs, the local behavior of zeros based upon continuity, and that's why we have such an efficient way to solve inequalities. That is something that is a luxury for us, and unfortunately, we have to start talking about it before we actually get to the formal definitions in calculus, so you won't be bombarded with so many techniques at one time. Trust me, once you get the definition, all of this will come full circle, and you'll see how the calculus really is the foundation of the mathematics that we have been doing. So what we want to do is to use the definition that we already have for the natural base. Here, notice I'm not using an n, I just used a z. But again, what we're seeing, we have 1 plus 1 over z. And then, of course, I have my z here, which I'll add. That's going to be the definition of E. But let's just see how we get that. Notice at this point, what we want to do is to produce a 1 over a z. So what we're going to do is take the reciprocal of this, and we're going to let z be n over r. Now, here's something that we've used before. If n is passing to infinity, so will z. R is just a fixed number. So as n gets incredibly large, so does z. So that gives us a correspondence that allows us to maintain the variable passing to infinity. And then, of course, if you notice here, we can actually solve for n. Just cross multiply. N is just z times r. So now as we go back here, we replace n with zr. And then, of course, here we just replace n passing to infinity with z passing to infinity. So now we have a function of z. Now notice, and this was what is important here. We have the laws of exponents, so we can just push the R out to join the T. And of course, the Z here that I wrote in is left behind. And now we have that formula that we saw when we defined the natural base. That is the limit as z passes to infinity of 1 plus 1 over z raised to the z power. That's the definition of E. Now, what's interesting about continuous interest is that it does make an improvement, but it's not a huge improvement. You rarely see it in financial institutions, but it is used on occasion. Normally we just think of amortization where we're working with a 12-month application of interest, like if you purchase a home or you purchase a vehicle, or maybe you purchase merchandise for your home, maybe some new furniture, which you amortize over 3 or 4 years. Maybe you even get lucky and get 0% interest. So that's another thing. One thing about finance is that if we are good stewards of the money that we have and we are practice at least some responsibility with it, we can actually establish credit worthiness in a very good way that helps us out. Because it's really nice when you can buy something on time and not have to pay excessive interest. So keep that in mind. This might be something that spurs you to study this more, at least if you think it will impact your life in a positive way. But of course, I'm biased. Math impacts everyone in a positive way if you're willing to study it. Now, notice here, this limit is now replaced with E. So we have P e to the RT. So when n passes to infinity, then it is removed from the functional equation. That is, n passing to infinity helps us to define the natural base E, and so E is the replacement. So we get a very simple formula, much simpler than the formula we started with. So now we can see future value, or the amount, when we have continuous interest, in this particular case, is now PE to the RT. Sometimes you can think of PERT as a way to remember that. Now, of course, you're thinking, what about effective interest? How do we get the corresponding simple interest rate for 1 year? Well, we do it the same way. And this formula, like I say, is even easier than the other one. Notice we take the simple interest future value, again, replacing the R with REFF, again, where T is equal to 1. Again, we do this for 1 year. And then, of course, the P's absorb. And then if we solve for the effective rate, we just get E to the R minus 1. So again, what we're thinking of is that we get the corresponding simple interest rate, and then that can be the rate that is applied once per year in a compound interest formula or a continuous interest formula. So again, we expect the effective rate to be higher than the given rate because it's going to take into account the compounding that has occurred. So again, you can often, if you ever do any finance analysis, for instance, when you think of actuarial science, which is very connected to mathematics and STEM, you can work for insurance companies where you actually set up tables where you analyze clients and you decide how to charge them for their insurance. And so it becomes a very important way to work with your clients and help them to make decisions that will allow their rates to be lower. And then you may use the concept of effective rate to make your explanations more palatable for your clients. Again, for those of you that find that you really enjoy mathematics and you think that that is somewhat taking over, the actuarial science is a great way to go. It's like becoming a CPA, you get an accounting degree, and then you become a certified public accountant. You get a mathematics degree, and then you become certified as an actuary. So it's really, really competitive in the sense that you've got to work really hard, but it's a certification that can be very rewarding. Now, let's see how we can use some of this. Again, these are very fun calculations, but I want to show you some ways to do the calculations so that they're clean and again, remind us a little bit of solving equations. Now, that's all the formulas that you will need to know. And what we want to be able to do is to apply the formulas correctly. So here's some examples from your homework that I think you'll find to be very straightforward and very interesting. Remember, when you're working with the financial models, there is some solution of equations, but it's minimal. What we want to do is use our understanding of these functions so that when we need to actually isolate a variable, we use the means that we have learned from studying the properties of the base A logarithm and the base A exponential. So here's an example. On January 2nd, 2007, $3,000 is placed in an IRA that pays 7.5% per year compounded continuously. So this is why we use the T and we use the N in the compoundings per year, or we use the T when we have the continuous interest. It just makes the formulas easier. Notice you never have to guess about the type of compounding. It will be explicitly stated in the problem. So now we know we have continuous interest, which is the PERT formula. And then we're asked to compute the future value for January 1st, 2022. So basically, as you see here, into the future 15 years, what will be the accrued amount? What will be the future value of our investment? And then B says, what is the effective rate? Again, what we want to do is to compute the corresponding simple interest rate for this continuous compounding. And again, that can be a very efficient way to understand what's going on arithmetically. So now what we can do, and this is a good way to do this, let's take our 7.5% and write this by definition. 7.5% is just 7.5 divided by 100. Now you can move the decimal and you have 75 divided by 1,000. So this will allow you to reduce these fractions. Notice 75 is just 3 times 25. And of course, there are 4 25s in 100. So that's going to give us 40 in 1,000. So the 25s absorb, and we just have an annual interest rate of 3/40, which is very nice. And of course, what I did here was just to compute the number of years of our transaction. Now what we can do is use the PERT formula. So you're not going to find the application of the formulas to be difficult at all. So now we have the principal amount, which is 3,000, and then we have E to the RT. Again, the R is 3/40, and the number of years is 15. And I just did a little sidebar here where we write the 15 is 5 times 3 and the 40 is 5 times 8. The 5's absorb clearly, and we just have 9 divided by 8. So we have a very clean expression. What I would recommend is doing the arithmetic here so you have a nice clean expression. It helps to make your work easier to read, and it is much more mathematical and exact. So at this point, you have an exact answer. And now you can move to your scientific calculator or your Google, whatever you use. I like to use the Google scientific calculator and simply evaluate E to the power 9/8 and multiply by 3,000. Now, usually in the financial calculations, ladies and gentlemen, we like to round to the cents. So you could run this out 4 or 5 decimals and then round to the 100th. Okay, so you've got dollars and cents. So what we see here is that we get $9,240.65. So again, do exact calculation, and we will see the same when we talk about the growth and decay laws that will also involve the exponents and logarithms. So what we have here is a way to speak to our clients. Your client will be very happy to see your computation, but they'll also be happy to see an effective approximation. Now, again, when you study the calculus, you're going to actually learn how your calculator works, and that will be the use of infinite series. So the arithmetic of the calculator is basically real analysis, and you will take 3 semesters of that as a STEM major. So you have a lot to look forward to. Now, the part B asks, ladies and gentlemen, what is the effective rate? So that's easy to do. Remember, we actually derived this. The effective rate for the continuous compounding is just e to the r minus 1. So what we can do, and we've done all the work, we've got our annual rate here, so we just say e to the annual rate, 3/40, and subtract 1. That's the exact rate. And then, of course, this can be approximated with Google. And again, when it comes to the annual interest rates, I would say probably 3 decimal places if you write it as a percent. So what we can do here is just run, 5 or 6 decimals and then write as a percent with 3 decimals after the decimal point. Again, if the problem is specifying a particular decimal correction, then please follow that. In most cases, we'll just say that when we actually state our problems, and then problems are stated in financial journals, they're usually written as percents. Now, of course, when we work arithmetically, we like to convert them to fractions so that we can have a more exact working or execution of our problem. So now what we can see, and this is what I wanted to show you here, notice this is the corresponding simple interest rate. So, and it's the same thing we did right here. If we go back and just say, we'll just levy the interest 15 times, once per year for 15 years, we notice now that we get the same thing that we thought we would. What replaces the R over N is just the effective rate. We apply it for 15 years, once a year. And so what we do is we just simply replace this in the equation, the ones absorb, and we're just left with what we thought we would get. This rate here, e to the 3/40. And of course, when we multiply by the 15, we just get the 9/8 as we have here. So you see the calculation is exact. You get the same thing. So that's why we talk about effective rate. We're thinking, what is the corresponding simple interest rate for the year? So if we just forgot the compounding, continuous compounding, and applied once per year for 15 years, that is compound interest, one-time application per year, we get the same amount. So it does not change the calculation. It simply shows you that when you check the annual interest rate here and the effective rate will necessarily be higher to take into account the compounding. So this is simply a way of readdressing how you report interest rates. And of course, as you get more sophisticated in your understanding of financial models, you will have other ways of looking at interest. But this is just a very interesting one where we see that we don't change anything. We simply just give a definition for the effective rate. And we see that if we apply this once per year for 15 years, we get exactly the same calculation. So there's nothing mysterious about effective rate. It's very sensical. So same future value for the effective rate applied once per year for 15 years. So I think it's neat how you can see that the definitions simply are consistent with what we've set up in our financial models. Now, there's one other example that I want to talk about. Well, actually a couple, just so you get a few extra examples here. And I wanted to have these set up so you could see how clean the work can be if you work with the fractions and the percentages in a way to keep your calculations exact. That's always a good way to do your mathematics. And it makes it very easy to state if you have to do any type of presentation for your colleagues. You want things to be clean and neat so that you can make an effective presentation. So now let's just look at the following example. I've got two examples here. A principal is invested at 4.5% compounded quarterly. So when we have quarterly compounding, that stands for 4 times per year. And then it says compute the time for the money to double. Now, of course, doubling there's nothing special about that. You could say triple, quadruple, whatever. You can replace this with any compounding that you like if you want to see 5 times as much, or 4 times as much, or 3 times as much. This is certainly not specific. You can change it as you need. So notice here, the first thing we want to do is to determine what is the fractional equivalent of the 4.5%. So just like we did with the last problem, we just write the 4.5% as a fraction by definition. This is 4.5 divided by 100. If we move the decimal, then we have 45 divided by 1,000. Now, of course, by the same number theory, 45 is just 5 times 9, and of course 1,000 is 5 times 200. So this just gives us a fractional equivalent, ladies and gentlemen, of 9/200. So now again, we go to our compound interest formula. Now the amount or future value is just 2 times the principal. We don't know in this particular case what the principal is because it doesn't matter. It will simply absorb. But first, what we want to do is go here and say, well, we need R divided by N. Here's R, and if we divide by N, we just multiply by 1/4 because we have compounding quarterly, or 4 times per year. Now notice when you multiply, you just have 9/800. And I did a little sidebar here. You can go ahead and get a common denominator and add the 1. Write the 1 as 800/800. So you get 809 divided by 800. That is a base. I'm not going to ask you to take base 809/800 logs. I mean, you could, but that won't be required. We'll just use a logarithm base that is accessible to us. Now, at this point, notice as I've written here, the p's absorb. And so you just have 2 is equal to 809 divided by 800 to the 4t power. So what I wrote here, ladies and gentlemen, is just to apply the natural logs. We don't have to do a specific base, and the natural logs are something that we have available to us in tables, or they're normally on our scientific calculators when we need approximations. So now if you apply the natural log, you can also apply the power rule. So you get the natural log of 2 is equal to 4t times the natural log of 809 divided by 800. Now notice, and this is important, if you want to isolate the t, you can do this. And so we've got, in this case, 4 times the natural log of 809 divided by 800. So to solve for t, you simply divide by this number. So if it's a little confusing here, just push all the constants together, and then it's easier to solve for t. So now you divide the natural log of 2 by 4 times the natural log of 809 divided by 800. And that is an exact configuration of the time. Now, at this point, you can now approximate using your logarithm keys on your scientific calculator. And when you do that, you will get approximately 15.4897 years. Now here we just have rounded to 2 decimal places, but again, whatever the problem requests of you, please do that. Again, what's important, especially when you're working with a client, is to do exact calculation. and then have one level of approximation. Or if it's the case, if you've got to store numbers, make sure you store numbers to a significant number of digits, that is many digits, so that you avoid the opportunity to get unnecessary round off error that can destroy calculations. And of course, with the ubiquity of computers, we are aware of that. And even back in the dark ages, when I first worked with computers, we were always made aware of round off error, that we had to always be aware of that in our calculations. So now what you can see, and this is again dependent on whatever a situation you have. If you got $1 million, I mean, 4.5% is not great, but it's not horrible. So if you have $1 million in 15 and a half years, you'll have 2 million. Okay, so of course, and you don't make any loans on your investment. Well, one thing about investing, if you're putting money away, there may be times when you have to withdraw some of it because you have other obligations that you did not count on. And that's just part of life. So one great thing about making investments is that you always have money in a secure place. And if you need to use some of it, it's your money. You can actually do that. There may be some tax stipulations that for which you have to abide, but the idea is that investing money always has your money in a safe place, and you can use it as you need. So again, just think of this as a more generalized problem where you can now look at this and think of the principal as being any value you want. And then, of course, you can change this to make it a better investment. Let's be very frank about this. We can't find percentage rates this high. I mean, when you get savings accounts and things of that nature, you'd be very fortunate to find this. But maybe there are good deals out there that you find and you can't pass it up. But let's just face it, in our economy today, things fluctuate, rates are variable. And so what we might find as good one day may not be as good the next. But this gives you a very nice example of how you can find the time for your principal investment to double. All right. Now, the last problem I want to talk about is just what I mentioned at the beginning of the lecture. That's present value. For instance, we're usually more concerned with a future value, but you think about putting money away in an annuity because you're interested in how much money you may need in the future. Okay. And so you're thinking, what does my investment need to be today or in some periodic sequence of investments so that I can accrue a certain amount at a future date? And that's what we call present value. And it sounds complicated like future value, but we know future value is nothing but the amount of the transaction. So what we want to do is just go backwards to solve for the P. Like I said before, P is often called the principal, but you can also substitute present value. So for instance, here's what this problem says, and this will help you to understand the way these problems are phrased. Compute present value of $1,000 after 5 years at 7% compounded continuously. So when we think of that, we're thinking in the future in 5 years, we want to have $1,000. So if we make one investment, what must that investment be so we have this amount in the time that's been indicated? So all we have to do is basically solve for P. Remember, for the continuous interest, because again, compounded continuously, you never have to guess about the formula. Never. You will always know what formula you need to use based upon the words in the problem. So that will never be an issue for you. So now we have the amount is equal to PERT, or E raised to the RT power. But notice now the amount is the 1,000. That is, we don't have the principal in this case. That's what we have to compute. So first we can go ahead and write the 7% as a fraction. That's simply 7 over 100. And of course, 7 and 100 are relatively prime, so we can't do much with that. So now when we look at our formula here, you're thinking you could just go ahead and solve for P and get a formula here. That's fine. However you want to do it, it will be adequate, whatever, as long as you use good mathematics. But notice here, we simply have RT 7 over 100 times the time, which is 5. So that just gives us 35 over 100. But notice the 5 absorbs into the 100 to give us 20. So we're just left with P times E raised to the 7 over 20 power. That's it. That's all we have. And so now, like we have over here, we want to solve for P. So we simply divide 1,000 by E raised to the 7 over 20 power. So exactly we get P equals the future value or amount 1,000 divided by E to the 7 over 20 power. So again, like I said before, you can go ahead and make your own formulas and just say, in this case, P is equal to A divided by E to the RT. And of course, you could use some negative exponents and just write A times E to the negative RT. It doesn't matter. I think sometimes it's easier to write it this way because it's a little bit more apparent about the algebra. Negative powers are very useful, but this is more than adequate. So now we have an exact expression here. So all you would need to do is get an approximation for E raised to the 7 over 20 power. Now what's interesting about these exact computations is that they can be a little bit mysterious. You have to think about what's going on with the problem. For instance, you know the E to the 0 is 1, so you know that this particular number here is greater than 1, but it's less than the value E. Okay, so we're actually going to get a number that's smaller than 1,000. Of course, that makes sense intuitively, but it also makes sense mathematically. And so when you actually run this to 4 decimals, you get 704.6880, which in this case, you can just simply round to 2 decimals. So what you can see, these problems have very realistic benefit. That is, the study of the exponential and logarithmic functions is very useful. Not only in STEM, you can see in financial models that if you do become a financier or an actuary, there's a lot of calculus involved in there. You basically have the natural base, which is the base of calculus that you have in the computations that you will do as a finance expert. So notice here, if we want to accrue $1,000 in 5 years at 7% compounded continuously, our initial investment would need to be approximately $704.69. So again, if you do take more financial classes where you actually discuss annuities and amortization, you will have more practice with this. I think this is always a good way to begin the study of finance. And if this is something that's very interesting to you, you can continue to take your STEM mathematics and then also take courses in probability, which are very, very useful in finance, especially when you have to forecast. So I want to be clear about this, and I want to be transparent in the sense that what you're starting to see is, as you study STEM mathematics, you see many, many topics coming into the study, that is, into the actual class that you're working on. Again, we want our mathematics to be precise. We want it to be well constructed, but we see as we study mathematics, not only are we looking into the utilization of mathematics in the medical arts, the engineering arts, the computer arts. I mean, there are so many disciplines that are impacted by STEM. And so now this is also acquainting you with the fact that finance is very connected to STEM. So enjoy these problems. Again, work through the derivations that we did in this lecture, just so that you're comfortable with these, and write these formulas down, just like you write down the identities for logarithms, as you write down the exponent rules for the exponential functions. Write them down on note cards, practice using them and committing them to memory, but with the foundation of the understanding. I think you'll find this to be very interesting, and this is always a topic that is fun to discuss. And you can actually discuss this with your friends who may not be as mathematically inclined as you. They would definitely be interested. Well, that's all I have to say about the financial models. You have a good day. We'll see you soon.